Hello everyone and welcome back to another video. Today we are looking at SpeQtral, who's promising to secure global networks in the quantum era. And if you want to know how they are actually planning to do that, then stay tuned, get yourself something to drink, and let's get ready into the website of SpeQtral. So here we are. This is the website of SpeQtral and it says securing global networks in the quantum era. How do they do that? So at SpeQtral, we are merging space-based transmission with terrestrial fiber to create a quantum key distribution communication network that will ensure absolute data security for governments, corporations, and tomorrow's most sensitive communications. So let's take a step back. There's a lot of information in that sentence and take it a little bit apart. So the target audiences are governments, corporations, and tomorrow's most sensitive communications. So why tomorrow? That's because it's showing that this is something which is applicable now. It's not like in 5 years, it's not in 10 years, it's now. And that has to do something with the concept of harvest now, decrypt later. What does it mean? What is it actually? So the idea is that today's communication, today's secure communication is secured by cryptography. And the algorithms behind cryptography, they are using some asymmetric difficulties in certain calculations. So it's easy to encrypt something, but hard to decrypt something if you don't have the specific key. And the reason for that is the prime numbers. So they're using prime factorization. So basically multiplying two prime numbers and then kind of factorizing them to decrypt. And this is a problem that is considered hard on a classical computer, but it is considered to be something that is easy to solve for a quantum computer. Well, you would say not a problem because today we don't have such a quantum computer, which is true, but we might have one in the future. And if you are today able to kind of sneak in, eavesdrop into an existing communication channel and copy all of this information, you can store it on a hard disk drive somewhere, keep it for later, and once you have the quantum computer, you can decrypt it. You can break the encryption, and that's kind of the idea. So copy information today, sniff into some communication channels, store it, and then later on when you have the quantum computer, you can decrypt it. And this is of course relevant for specific type of information. In some cases it might not be such a big problem. In other cases where the information has to remain secret for a long amount of time, it is. For example, when it comes to your health data, that should remain secret for the rest of your life because you should be the only one to access it and the authorized parties, but nobody else. The same for governmental data like secrets of the states or corporations that might keep your secrets, for example, as an end user, or that have a secret source recipe, like, I don't know, Coca-Cola's secret recipe behind the drink. If that gets kind of exposed somewhere, okay, then everyone can replicate it, so then it's not secret anymore, and that's a vital risk to the company. So this is kind of the idea. The solution is this idea of quantum key distribution. So by that you mean you basically create this encryption key, which before was a prime number, on a quantum channel. And the advantage of that is that by the principles of quantum mechanics, you cannot sniff into that without having the parties that want to communicate with each other recognizing that. So this is because of the fact that you cannot clone quantum information, so you cannot just create copies like in the harvest now, decrypt later, because then the two parties that are communicating via the secret channel, they will know that somebody's thing in between. So this is the idea. And what is interesting now and what is setting SpeQtral probably apart from other players here is that they are merging the space-based transmission with terrestrial fiber. So we have heard of both of them kind of individually. So there are companies that are looking into using optical fiber from communication as of today, like from the telecommunication centers that we have today, from the supercomputing centers that we have today. You might know that they are connected with fiber. And the idea here is that you use this existing fiber to create a quantum channel where you are transmitting photons, which are quantum particles, to kind of create this entangled, decrypted, encrypted system where you are distributing this key. The same is true for space. So there have been cases where people have been, I think there's a famous one from the Chinese Research Academy that said that they have established a way to communicate in a quantum channel or to build up a quantum key distribution in space using satellites that communicate with each other and with a ground station. And now here with SpeQtral, they say, let's merge both. And let's dive a little bit deeper into how this is going to look like. So SpeQtral's global quantum safe network. It consists out of 3 steps. Here you see all of them have a time step 2024. So from where I'm recording this, which is beginning of 2026, 2 years ago, then 2025, which is last year, and 2026, which is this year. And how does it actually look? So the first step was to establish a quantum safe terrestrial network. So SpeQtral, in partnership with telcos, telecommunication providers, is implementing fiber-based quantum key distribution solutions for metropolitan communication networks. Then the second one is on the satellite, right? So quantum safe global network. Satellites generate and transmit unhackable symmetric quantum keys used to secure existing communication infrastructure over long distance. So here the advantage is that within space you can communicate over much longer distances. And maybe also here let's take a quick step back. So we have seen companies in this fiber space already, and most of them report that they can go up to 100 kilometers. Now 100 kilometers is fine if you want to communicate in a city or in a small country like, for example, Switzerland, where I'm based. But if you have a large country like the US, like China, then you need to have something that can communicate over longer distances. You might even have like island places where you don't have a physical fiber connection. And that's where these satellites become interesting. So why can satellites provide that and fiber cannot? I think, and I'm not an expert on that, the reason is because fiber is basically a solid state system. So over time you have heat changes, so the temperature is changing of the fiber. There might be some strain, which is kind of changing the optical properties of your fiber. And looking at those companies, they already have figured out some algorithms to adjust for that over time, because otherwise your yield in the quantum key distribution goes down after a while. So you need to be able to have a smart way to compensate for that. And of course, the longer your fiber, the more difficult. Plus, in addition to that, since the photon is traveling through an optical fiber, there's a chance that it gets absorbed, which normally for communication might not be a big issue because you're sending a lot of photons. But here in the quantum information, it's really about single photons or single quantum states that you are distributing here. So if you are losing them on the way and the probability of losing them gets higher the further, like the longer your distance is, the lower your yield. So that's probably another issue here. In the case of satellites, this is a little bit different because they are up in space. So there is nothing, there's just vacuum. And light traveling in vacuum is actually much more efficient because, first of all, for communication reasons, it's traveling a little bit faster than in a fiber. That has to do something with the optical properties of light in this fiber matter. But this is not the most important thing here. What is important is you don't have a medium that can technically absorb, so you can send a photon over a long distance without any interference with something else. And I think that's why combining those is very interesting, because now you have a way to communicate over long distances and something that can communicate very effectively, probably at much higher rates, and can, let's say, be localized much easier in a terrestrial network, because the fiber infrastructure is already there. You just upgrade something. Whereas for this one, as we will see in the next stages, you need to add some additional infrastructure. And then finally here in the third stage, 2026, it says a global quantum fabric. This represents a collection of hardware and software systems that seamlessly integrate the quantum-safe satellite and terrestrial networks. So basically combining both of them into one system now. This is the first, I think, satellite solution that they launched. So in June 2019, the SpeQtral's was deployed. SpeQtral's, of course, with QI was deployed from the International Space Station. I think this is like a micro satellite type of object. And then here it explains again what I've already talked you through, this idea of harvest now, decrypt later. And this is, I think, the fiber network. So fiber-based quantum key distribution for metropolitan communication networks. And you see there are like multiple endpoints here indicated by these queues. And they are all part of this network and can communicate with each other. And then, okay, how our QKD solution works. Our integrated approach to quantum communication, including terrestrial and satellite QKD technologies and PQC, so sets the foundation for the backbone of a global quantum internet. Then quickly looking at this example here. So here's what it would look like. Think about two banks that want to communicate in two different locations. So one of them being in Singapore and the other one maybe in Great Britain. So what would happen is you would take this data and then over the terrestrial network, so over the fiber, you would get it to the next spectral ground station with a spectral quantum key distribution system that is a QKD that is supported by these devices that connect to the fiber. Now coming from that, it would go into this ground station here, where it would then connect to a satellite via this spectral quantum key here, and then it would communicate between the satellites via the spectral quantum safe satellite network, go back to the next ground station somewhere in Great Britain, for example, and then via the fiber go to the other bank. So that's how you would have an end-to-end kind of quantum encrypted communication channel between two parties. Here is a little bit about the progress. So the timeline, what has happened so far, 2012 to 2018, miniaturizing quantum systems for space. So their background is the original discovery is in the space development, developing and building satellite technology to demonstrate quantum light sources in space at the Center of Quantum Technologies, CQT. Then I think that's what we've seen already. The satellite launch of SpeQtral's successfully produced an entangled photon source in an orbiting cube satellite. So that's the SpeQtral's. Then it goes on 2020 to 2022, point-to-point fiber QKD deployments, so teaming up with Toshiba Digital Solutions Corporation to set up live QKD link demonstration across Singapore. Then this was, let's say, built up into a network. So quantum communications network deployment in 2023, building trusted nodes across Singapore to build a national quantum safe communication network. Then in 2025, so this is last year from now, the goal was, and I think this is a little bit outdated still, to launch a quantum satellite, so generates and transmits entanglement-based unhackable symmetric encryption keys globally to secure existing communication infrastructure. And then in 2026, so for this year, the goal is to build this global quantum fabric, the integration of multiple spectral satellites, terrestrial networks, and software solutions for global end-to-end quantum safe communications. Then down here we find the latest news. I'm recording this beginning of 2026, and here it says the latest one, free space quantum communications trials set the stage for satellite missions in July 2025. Then there's some information here about the investors, known ones like, for example, Golden Gate Ventures, which is at least a name to me, and other ones as well. And then down here we see the companies based in Singapore. Let's quickly hop into the news section to see what else is new here. So we see here a news from November 25. So this is a very recent one, and it says SpeQtr, the entanglement-based quantum communications demonstrator satellite, is now on orbit. Let's quickly hop into that. So it says SpeQtr, the entanglement-based quantum communications demonstrator satellite, is now on orbit. SpeQtral's REL quantum communication satellite successfully launches on SpaceX Transporter 15. So SpaceX, the American space company. Singapore-UK quantum collaboration begins on-orbit commissioning following successful deployment. Singapore and Oxfordshire, UK. SpeQtral, Singapore's leading quantum communications company, in partnership with the UK Science and Technology Facilities Council, REL Space, announces the successful launch and deployment of the SpeQtr CubeSat aboard SpaceX's Transporter 15 mission. The spacecraft, containing SpeQtral's space-qualified entangled photon pair source and detector modules, was deployed into sun-synchronous orbit on 28 November 2025, marking a significant milestone for Singapore-UK space collaboration and quantum communications technology. And here we see the satellite, so that's what it looks like. The SpeQtr A12U CubeSat, containing SpeQtral's quantum payload, is set to demonstrate space-to-ground quantum communication. And then here it says something about the general idea, I think. So advanced quantum communications technology, commissioning phase begins, addressing cybersecurity challenges, Singapore-UK partnership, operations, timeline, and looking ahead. So let's quickly go through this. Following the commissioning phase, quantum communications experiments are expected to begin early 2026. The mission will start by conducting experiments with quantum-enabled optical ground stations at the Center of Quantum Technologies at the National University of Singapore and at REL Space's Shepperton Observatory in Hampshire, UK. Data from these experiments will allow for demonstrations to secure communications between the two sites and inform development of future commercial quantum communication satellites. As quantum computing capabilities advance, the need for quantum secure communications becomes increasingly urgent for governments, financial institutions, and critical infrastructure operators worldwide. Success in this mission will demonstrate the viability of cost-effective small satellite approaches to quantum communications, potentially accelerating deployment of commercial quantum communications constellations while establishing important precedents for international cooperation in quantum technologies and space-based security systems. So we see that was quite a big step here, and we are expecting, or they are expecting to have first results early this year already. Let's quickly take a look at the products as well. So what type of products do they sell? I mean, looking at the trajectory so far, I think mainly it is going to be a service-based model, right? So you can buy basically quantum key distribution from them, so secure communication channels, very much like a VPN provider, but quantum. But apart from that, there are also physical products. Here it says use SpeQtral's infrastructure as your service for work with us to build your own dedicated infrastructure. And that's, I think, where the products come in. Here you see Spookies, own your own QKD satellites. So they're selling the satellites, the same ones that they are launching for their own network. So based on SpeQtral's satellite design, we can deliver a dedicated QKD satellite or a constellation of satellites designed to support entanglement-based as well as prepare and measure-based quantum payloads. Spooky satellites offer tailored solutions for sovereign customers aiming for the security of their most sensitive communications. These satellites use cutting-edge quantum technology to generate and deliver unbreakable encryption keys directly to optical ground stations anywhere in the world. We even handle the orbital delivery for you, so you can focus on what matters most, building secure communication services tailored to your specific needs. And I guess here the main customers are the ones that can really afford, let's say, a global satellite network, and that is probably mainly big states or unions of spaces of states like the European Union, as well as super big corporates. Like you could probably imagine that if you are the biggest bank in the world, you might be able to afford something like that, or one of the biggest banks in the world. Okay, besides that, then we see here quant optics. I think this is the optics that goes into the satellite. So want to add QKD to your own satellite. So this is more on the optics side. Could probably also be interesting for research applications, and of course for people that are building satellites and are looking into adding new types of features into them. Then there's SQUINT over here, SPEQtral's polarization entanglement photon pair QKD system. So this is basically at the heart of the QKD quantum key distribution system. It says with small form factor of 1 unit, each entanglement photon pair generation rate up to 45 million and qualification complete for space. Okay. And then there is TARKIS, which is the ground station. So this is basically what you need to be able to communicate with the satellite. And this is what you need to put onto all of the endpoints. Here it says introducing TARKIS, SpeQtral's mobile quantum optical ground station designed for deploying ultra-secure quantum network infrastructure at essential locations like data centers, financial institutions, and government entities. With a modular and portable design, TARKIS allows seamless network upgrades at any location requiring only an unobscured view to the sky, standard power, and an Ethernet connection. Key features include support to BBM92 and BB84 protocols, automated telescope functionality, robust satellite tracking in challenging weather, and a built-in office with a server rack for edge deployment. For customers ready for permanent or rooftop installations, we can either retrofit existing optical ground stations or build a new one at your preferred location. And then there's also here the backend quantum unit. So the BQU is designed as a plug-and-play solution to enable existing optical ground stations to seamlessly receive quantum signals. So this is basically what I think is needed also in here to kind of come from, to connect those different systems with each other. So you see, they are also selling the components that they are building, and this is actually something that we've seen also across other players in the market. Oftentimes they're not only aiming for the final product or the final service, but also selling the technology that has been developed along the way towards that final goal. So I think that's a very interesting approach here as well. Let's quickly check out the satellite QKD, because the other one we've talked about quite a lot. So I think here we see the different types of satellites. So SpeQtral's, then we see SpeQtral, which has been launched, which is already quite a bit bigger than the previous one. So this was 3U. I think this is units as in like a space unit for the size of a system. So this one is already 4 times larger. But it also comes with an entangled photon source and single downlinks. So this time there's also this downlink to communicate with a station on the ground. And in 2026, so this year, there will be the SpeQtral's. SpeQtral's is a commercial tech demonstrator mission with the aim to validate global QKD distribution from space. The satellite will test and validate QKD using BB84 as well as BBM92 protocols, and then weak coherent pulse source, entangled photon source, and the single downlink. So there we see that now there's, in addition to the entangled photon source that is now there's also a weak coherent pulse source in this one as well. Okay, let's quickly check out the team behind the company. So here we see the team of at SpeQtral. It says SpeQtral comprises of a group of experts in quantum physics, aerospace, communications, optics, and systems engineering. And then here you can meet the team. You see the founders, for example, here, and I think the board of directors. They all have very different backgrounds, as already mentioned up above in the description. So you have people with a physics background, other ones that come, let's say, with a more engineering background. I guess there's also people with more, let's say, business-focused background in this team, in this board of directors as well. And then the call to action to join the team. And I think with that, we are already at the end of today's episode. If you liked it, then please use the hype function below the video so that other people get aware of this as well. If you want to see another one of those videos, make sure to check out our playlist on our YouTube channel, which is the Hidden Quantum Champions playlist. There are more videos of companies like this and other companies from the quantum ecosystem. And with that, as always, make sure to stay hydrated and see you in the next one. Bye bye.